My name's Paul Kurmas. I'm Director of Strategic Product Development at a small company called Mutualink. We've had for about 12 years, we've had deployed a system that creates multimedia communication between multiple public service agencies. I'm just going to go through real quick and give you a sense of what we're doing now and why we've come to Redis. And I could subtitle this talk, What You Learn When You've Got 10 Years of Catching Up to Do on the Rest of the World. So our goal is pretty simple. Communications in incident response saves lives. When police departments roll up to a school where there's an intruder, where there's an active shooter, if they have situational awareness, if they can see what's happening inside of the building, they are prepared. They know how to respond. They know how to deal with the situation. Without full information, they can't. And most of the current solutions that exist don't support multimedia. So I'm going to zip through and talk about our overall model is to not replace our customers' existing systems. Our customers have communication systems like radios and video systems. We provide a way for those to interconnect into an internet-based solution. Easy to use interfaces, don't require a lot of high-end training. We maintain security and we maintain sovereignty, which is a word we use to describe the political problem of multiple police departments, multiple fire departments, and so on, wanting to participate in communication, but not wanting to give up control of their equipment because they're very control-centric. So what we're working on right now is our 4th generation product. Our very first generation product comes from the embedded systems type space. It's purpose-built software running on a purposely deployed computer, communicating over a VPN. Our 2nd generation, we said, hey, let's take our 1st generation solution, slap that embedded software in a server, run it 50 times over, call that a scaled system. 3rd generation, we said, okay, let's put those computers in a data center. And now it's a cloud. Wow. So, but the problem that we faced for my team about a year and a half ago was that we were given the challenge of increasing the scale of our solution by a factor of 10 to 20 times with a lifetime goal of going to 100 to 200, creating standardized APIs, reducing our hardware cost by over 90%, maintain compatibility with our existing products. And what we did was we chose to move to current best practices, redesign the system completely. Don't try to adapt what we had. Use a microservice architecture. We're going to use Redis as our primary data store. Our application would implement web APIs, access Redis to pull out the data as it needed it. Just as we started developing, they came back and they said, oh wait, we don't need to go 10 to 20 times now. We need to go 100 to 200 times immediately. And we want a lifetime goal of 1,000 to 2,000x. Our new target is an architecture that's going to support 10 million users simultaneously participating in this network, and then some occupancy rate of the actual media. We were also given the requirement that the system be always available. We had to have active functionality. No primary data center site, no backup data center site, and a switch over. Everybody's live all the time, and your mobile phone or your computer could be suddenly rerouted over the internet to the other data center, and all of the operations needed to succeed just the same. So we realized, number one, I've got a team of about 15 people. We realized we don't have time to create a multi-site synchronization protocol. We don't have time to design it, we don't have time to code it, we don't have time to test it. And Redis as a backing store for the data, for the primary data store for the program was necessary but not sufficient. Fortunately, at about that time, the CRDB functionality had just been announced. Got to know the folks at Redis Labs, got a lot of great support from solutions architects, Jake Ungerman especially, and got a lot of guidance on how to use CRDB as a primary data store for the active-active application. I'll share briefly a couple of our primary use cases that really called out the challenges of number one, being newbies to Redis, and then number two, figuring out how to fit that into the CRDB model. The first use case we call a collaboration, and the collaboration is a amalgam of the members of a multimedia conference. It's the media that makes up that conference, which can include audio and video and text messaging, file sharing, and other things that our customers may think of, and the business rules that apply. And I fell back to UML just to give the simple example of, okay, here's the objects I think in terms of. It's fairly simple, you know, an object with a couple of collections. So we let our development team loose on this, and the very first solution they came up with was based on the belief system that Redis is a key value store. Oh, you know Memcached? Yeah, Redis is that and better. So the first solution was, we'll just serialize the object as a JSON string and save that bad boy in a string object, and our work here is done. Pretty CPU intensive for the serialization and the deserialization, but absolutely tragic when it came to the CRDB model. Because CRDB and the types in the conflict-free resolution data types depend upon a policy for how conflicts are resolved. And for something as trivial as a string and an operation on the string as trivial as set, there's only one policy resolution, which is last writer wins. With multiple active sites, boom, you're going to lose data. So it was back to the drawing board. It was reading the documentation, and it was discovering what everybody working with Redis over the last 10 years had probably already learned, which was data types are your friends. And so just as an attempted cataloging of the thought process, we had to learn to think in terms of arranging the data in Redis in an efficient way. And it's efficient whether you're running just in a local environment or if you're running in a multi-site environment. So what we ended up creating instead was every one of those objects is represented by a hash map, but the lists of members are represented by sets. So now our software has to construct a hash map that describes the overall collaboration, but it references out by key, or it can derive the key in most cases, the list of members, the list of media. Those collections can be manipulated independently. The media objects can be manipulated independently. The media objects can be manipulated independently. So we eliminated the last writer wins conflicts, and we focused in on solving our application's problem. In our application's case, we don't expect hundreds of new members to be added every second. We expect, I'm going to go invite somebody. I'm going to invite another somebody. Somebody may drop out. There may be 1 or 2 modifications per second, and they'll tend to come in small bursts. So as long as we have a functioning multi-site synchronization through the careful selection of what the keys are from the proper use of those CRDTs, we're able to maintain a consistent representation of who's in this collaboration, what media is available in this collaboration, and withstanding the momentary cost of synchronization when something is added at one site for it to appear in another. And in our particular case, we've reviewed what the synchronization failures look like and asked, can we tolerate the behavior when there's that loss of synchronization? We don't see a new member in one site for a small period of time, or we see a member who's actually dropped out for a small period of time. And we decided, yeah, that's a tolerable issue. In fact, it's an issue we have with our current product. My second application example, after the keynote, I'm going back to the team after this week and I'm telling them, yeah, let's try all over again with the next version of Redis, because it is a classic time series data problem. One of our media streams that we handle is a datagram. It's simply a stream of payloads of some type presented by some participant at some time. And the one wrinkle on that is that customers' business rules may set a limit on the duration that data will be kept in memory. That limit might be as little as 5 minutes. The whole idea of it is not to keep an archive of the conversation, but rather just to hold the data in memory long enough for anybody whose mobile device is lagging in receiving and processing push notifications, to give them a chance to come and get the data and stay up to date with what's happening. So again, with the UML, nice simple example. It's just an object with some metadata at the top, and it's calling out a collection of the specific datagrams. And having already discovered the CRDB, we realized that this was, again, a case where we needed to look at our list of supported types and then use the types efficiently. So we end up creating a hash for each of the datagrams that gets posted, keeping the payload of it, keeping the MIME type of it, keeping who posted it, but the when it was posted goes into a sorted set. And we're depending upon the sorted set to maintain the stream of messages. And we solved the business rule of data expiring after a period of time by using Redis's expire capability, marking the object as volatile. So that's the posting side of the problem. The retrieving side of the problem, we're assigning each of the clients a small piece of cleanup work. And that cleanup work is to visit the sorted set and purge out any records that have expired. Because of the expire operation on the hash set, we know that any object that's past that business rule deadline is already gone. But the UUID, the key of that record, is still hanging out in that sorted set. So we're slipping off to the clients the responsibility of purging off the list. Then we use the Z-range by score to pull all of the messages since a starting time, since the last time that client asked for messages, to the end of time, and we get back the list of keys and the time that the message was posted. Now the client can indirectly, it makes that call to the hash, gets the record. Now it's got the sender of the message, it's got the payload, it's got the MIME type, knows how to render it. The learning for us with this is to continue learning Redis and to continue learning the data types, learning what's supported. For example, just today with the keynote, this is a great candidate to be reworked using the time series data type. We do realize a synchronization problem here with the fact that synchronization is a non-trivial operation, which is that a message may be posted at one site and not yet replicated to the other site. But a client that gets the push notification quickly from the site where the message was posted, but is being served by the second site, might do a get and not get the message. So we're allocating to the clients the responsibility to clean up from that mess. We can't fix everything with the CRDB, but we can give the clients the opportunity to come back and realize that they missed data and make another fetch. And as long as that happens before it expires, then the situation is resolved. But the thing that's really challenging for us is not resting on the current implementation. One of our key problems that we're still dealing with is that having a multi-replica microservice model, we have a lot of cases where we want the program to respond to some event. And PubSub within Redis seems like a great way to distribute those events. But when you have 10 instances of a service running and they're all subscribing to the same PubSub queue, they're all going to get that event. And in some of our cases, that's exactly the behavior we want. In some of the cases, we only want one instance of the microservice to respond to the event. And so we've had to create temporary solutions where we have an elector strategy. We elect one instance of the microservice to be in charge of that work. He's the only one listening to PubSub, but that defeats the whole purpose of the multi-replica model. Sure, if he fails, we can re-elect a new leader, but we're eyeing a redesign of that around the stream data type as a way of distributing work to microservices as the stream becomes type that's supported within the CRDB. And even then, there will be some synchronization issues due to the fact that you could end up with a service dequeuing, claiming work out of the stream at both sites at the same time, and having that not be synchronized. We have another key piece of data that our system is maintaining is geographic data, which has not yet moved into CRDT status. So right now we're having to maintain the geographic data in a separate non-CRDB, a local cluster, and coordinating the movement of data between CRDB and the local. We have a couple of other upcoming things that I failed to list here, but a key one is integrating the graph. Right now we're maintaining a subscription table for our clients, keeping track of thousands of clients wanting to subscribe to events on thousands of different things. I tell my team in trying to describe it, it's our own private version of Twitter. And we're implementing it by brute force right now. Why are we implementing it by brute force? Because we simply haven't had time to learn the power of Redis. We haven't had time to learn every one of the data types. So that'll be revisited as a CRDT. I described at the start also that we're a multimedia platform. Generally speaking, for performance of live media, putting any of the data through a data store would create way too much latency for the product to be useful. However, we have applications where we need to buffer media for a short period of time. One, to support clients who might be late to the game and want to replay the last few minutes of audio conversation or of video conversation. So we envision connecting our audio processing and our video processing into creating an HTTP live stream service and having the HLS backed by Redis, fragmenting the data into a couple of seconds of media at a time, and pulling that out as available. So for us, key thing that I really wanted to focus on is the lessons that we learned being new to Redis, being new to the CRDB, was that we've learned it's incredibly important for us to be completely aware of what our applications classes do, what their data is and what their operations are. You'd think that that would be table stakes, that you'd expect software developers to do that, but we have to remind ourselves all the time. And to know the Redis types, especially the CRDTs, and not think of Redis just as a key store, but think of it as a living, breathing engine that can implement our objects for us. And then find that mapping. Figure out how we can use Redis to do the work for us instead of implementing all of the work inside of our services. I have about two or three applications that I see us going back and redoing with Gears once that gets released. And then for our application, for it being a widely separated active-active model, need to ensure that we identify all of the possible conflicts, that we understand what the trade-offs are, that we mitigate the trade-offs of the potential conflicts, or that we eliminate them. And just own our problem, be completely aware of what's happening. That is it. I think I even kept it in on the 20 minutes or so. But happy to take any questions you have, or have any conversation with you about how we use Redis or with our problem space. And thanks for your attention. I may need headphones for that. Can I get a pair of the headphones that are on? Yeah, I'll probably hear him, but.
Hi, thanks for the talk. That was great. Can you go into a little more detail about if you faced any latency issues with synchronization while using CRDBs and any challenges that you faced?
Yeah, good question. So we have and we are still facing some latency issues. Our latency issues so far have to do mostly with mastering the configuration of the tool. The Redis clustering, even locally, is non-trivial for operators to get the configuration right, and we're still working on having the full synchronization up at production level. We're in development in QA state now. Our current product depends upon a virtual private network connecting our servers and routers, creating the VPNs across multiple data centers. So we're already in multiple tier 1 internet providers. So we do track our interruptions and our losses as service, and those tend to be limited to a few minutes a month. You know, we end up seeing the occasional network reconvergences. Our track record typically is that we have about a 50 to 100 millisecond maximum latency between the sites. So we expect at scale the inter-site latency is only going to be a quarter second to a half second maximum. That's what we're budgeting on, and in fact, it still puts us a couple of orders of magnitude better than our current product solution, because we're depending upon a very slow retry strategy of unicast and multicast messaging across our private network. But we are putting a lot of eggs in the basket of getting the eventual consistency from the CRDB. We're just counting on the time frame of it being sufficient for the application. I kind of talked around it, but I hope that answered. Anything else? Okay. Yeah, actually, I'm looking forward to being back next year with more charts and more and more experience, because this has been it's been a real adventure for my team, because it's the core team working on Redis has been about 6 people, and it's in total, it's the largest project my company's ever taken on, but it's still a very small team compared to other software projects that I've worked on, and there's a lot here.
First of all, thanks for the very interesting talk. Second, can you refresh me the main reasons for selecting Redis versus other NoSQL database managed systems? And third, do you think that having chosen a different one would have you less problems or less obstacles?
Good question. We chose Redis initially as a local data store, and we were already quite invested in it as a local data store. The speed was important, so we wanted to stay away from anything that was a disk-based store, and then a lot of times the recommendations that I made ended up coming down to the level of support we could get and the level of availability of the component in a number of different environments. For us, a key one on that multiple environments was the ability to scale up to the cloud and the ability to scale down into a smaller embedded system platform. In the embedded system platform, we wouldn't be using CRDB, but we wanted a tool that would be functionally identical as we moved up and down the scale. I had colleagues that advocated for MongoDB and so on, and we just thought there were too many compromises in trying to make that work compared to what Redis was providing. All right. Thank you very much.